So next topic is dielectric antennas. So dielectric antenna technology has been evoluted. Initially in 1950s and 60s, it was used to it is used to have used for dielectric resonators are used for microwave filters and microwave circuits, not for antennas. After Long, Professor Long, uh, he has uh, he has excited the radiating mode of the dielectric material for epsilon r value greater than 8 to 100. He has taken around 15 or 20 in that particular paper. And in 1981, Professor Long, 1983, I think, has proposed that the dielectric materials can also radiate like patch antennas. With even though the antenna is bulky in nature, but the advantages are more when compared to the patch antennas. The advantages are bandwidth is more, and also whenever if you see if epsilon r is increasing, so frequency is the bandwidth is proportional to inversely proportional to epsilon r. So epsilon r is increasing, bandwidth is sorry, if the whenever the epsilon r is increasing, frequency is going to be reduced. So the whenever high dielectric materials are used, the frequency is going to tend towards the lower frequencies. And the why the bandwidth has been increased is generally in microstrip antenna, whenever there is a metallic antennas are there, there is a spurious field radiation. That means whenever a light is scattered on a metallic plate, it is going to scatter in different directions. So like that, the radiation is going to be scattered across that particular plate. That means that radiation energy concentration at particular point is very less. But if you use a dielectric material, a ceramic material, the radiation is going to confine to its surface. If it is cylindrical in nature, the radiation is confined to cylindrical nature. If it is rectangular in nature, the radiation is confined to the rectangular in nature. So that likewise, the radiation is whenever that radiation is confined to the nature, then it is going to radiate more. So that bandwidth is going to be more. That is what he has explained in this particular theory. So there is a lot of theory behind it, and there is a lot of finite element method analysis is also there in the Aldo Petosa and Luke and Leong book, and you can go through that. Those two are very beautiful books. Here, let us classify these dielectric antennas. Generally, basically, there are narrowband dielectric antennas are also there, and broadband dielectric antennas are there. And there are another categories, dielectric loaded antennas are also there, and dielectric excited antennas are also there. And finally, there are hybrid dielectric antennas are also there, right? So next. So this is what that was talking about. Radiation mechanism in a dielectric antenna is a displacement current circulating in a dielectric medium, usually in a desired shape of ceramic block. The stored energy inside the dielectric is extremely high, and it is difficult for the external objects to detune the device. The bandwidth of resonant device is a function of loaded Q, which is controlled by the how energy is coupled into and out of resonant device, and is under the control of the designer. So you can control your design, right? So the unloaded Q is a measure of the internal losses in the device, and device which is high unloaded Q may be used to create an antenna structure with low loaded Q quality factor, and wide impedance bandwidth is going to be achieved. So the broadband dielectric antennas can be obtained by suitably configuring the feeding structure. The primary radiating component of dielectric loaded antennas is a conducting element. The dielectric just modifies the medium, imparting important performance advantages. Dielectric antennas can be used to excite parasitic copper antennas or vice versa. In this class of antennas, often the conductor forms the major radiating part of the antenna. There are bandwidth advantages in the dielectric copper hybrid approach of the dielectric excited antennas. So here, all the categories of these dielectric antennas are explained, how they are excited and how the bandwidth is going to be achieved and everything, right? So finally, the dielectric resonator based loaded antennas and excited antennas comes under category of hybrid dielectric resonator antennas. Let us examine through the pictures, right? Next. So let us see the advantages first. The DRA is an antenna that makes use of radiating mode of dielectric resonator. It's a three-dimensional device of any shape, and hemispherical shape is also there, cylindrical, rectangular, triangular, etc. Like what we have done with the patch configurations. And resonant frequency determined by its dimensions and dielectric resonator, a dielectric constant epsilon r. there is a degree of freedom here, right? You can control the shape of the dielectric resonator, that is by height of the dielectric resonator and radius of the dielectric resonator, radius or edges of the dielectric resonator. So you can, there is a degree of freedom. You have to study the parametric survey. You have to do the parametric review. I mean, a study, you have to do it. Otherwise, that degree of freedom, you can use it and you can bring it down to the desired frequency of your application. Right. Next. So dielectric antenna is mostly used for the millimeter wave frequencies, and also there are other modes like TM01 delta and TE01 delta and hybrid modes, hybrid electromagnetic modes 11 delta. So delta means it is a longitudinal variation of this particular feed is going to be analyzed through the delta. So if it is 3 means there are longitudinal mode generation will be 3. 3 modes, 3 additional modes through longitudinal variation will be there, right? So I'm going to show you through the picture, right? Next. So these are the finite element method analysis in order to find out the fundamental resonance of cylindrical DRA, because most of my work is concentrated on cylindrical in nature. So the 3 modes, TE01 delta, TM01 delta, HE11 delta, I've given the formulas. So first you have to find out the fundamental frequency by knowing fundamental dimensions of the antenna, by knowing fundamental dimensions of the resonator, by knowing the frequency and also epsilon r values, right? Next. So let us see the basic operation of the dielectric resonator in a probe-fed dielectric resonator. If you see this dielectric resonator, in the first figure, the probe was attached to the DRA, just directly attached to the DRA. So if you take the right hand Ampere's law, whenever there is a current carrying conductor, there is a magnetic field around it, right? So if you take that probe as a current carrying conductor, the magnetic field will be around the conductor. That around the conductor magnetic field will be penetrated into the DRA, right? And the magnetic field will be penetrated into the DRA, and exactly opposite 90 degrees to it, electric field will be there, right? Whenever it is radiating mode is excited, obviously whenever there is a electric magnetic field is there, 90 degrees electric field is also will be there, right? That 90 degrees electric field, whatever it is there, it is trying to escape from the DRA. That is how radiation happens, right? So next. So let us observe this modes. If you see the earlier picture, how the magnetic field, the solid lines are magnetic fields, and perpendicular to it is electric fields when TE01 delta mode. When TE01 delta for in the B figure, TM01 delta mode is see the dotted line is the dotted line is a magnetic field, and solid line is opposite to that. The TE, TMR both are going to be exchanged, right? Like that. So HEM11 delta, if you see 11 is, one is for electric field and one is for magnetic field. The delta is for the longitudinal direction. There is another mode is going to be created. That is delta mode. That is given in solid rectangular in nature. Okay. Next, if you see HEM113 delta mode, so one is for electric field and one is for magnetic field, and another one is for delta mode. That is 3 modes. 3 modes are in longitudinal directions. 3 modes are generated. So that is how this work is completely explained by very good by the Raj Kishore and from ISM Dhanbad and Ravi Kumar Gangwar's papers. If you see, these modes will be very clearly explained theoretically and also experimentally, right? I think it is better. It is better if you go through these papers, you will be understand very well, right? Or else you can contact me later. I'll explain later, right? Thank you. Next. So this is how the dimension of the DRA is going to be the find out. I mean, the frequency is directly proportional to the. I mean, the dimension of the DRA is proportional to the lambda by epsilon r, right? Anil, the presentation was, yeah, right. So the next is next. So there are different DRA shapes are available in the market, and you can use any of those. You can see these are ceramic materials and other materials. You can use it for the direct resonator antennas, all the kind of direct resonator antennas. Next. So advantages is low cost and low loss. I cannot say it is a small size, but you can make it small size when along with microstrip. Like you can make it as hybrid nature, and you can make it all small size. But as you know, ceramic materials are lightweight. It's a lightweight antenna. The bandwidth is more than when compared to the microstrip antennas, which is more, and the epsilon r values for this dielectric antennas will be used from 8 to 100, but now it was there are also people are using from 6 to 100 also. And excitation methods are all are same as microstrip antenna. There is one additional excitation method is available in this particular dielectric antennas, that is dielectric image waveguide method. Dielectric image waveguide method means you're going to excite one DRA, and parasitically you're going to place another DRA, and through this DRA, that dielectric radiation image is going to be created on another DRA parasitically. So that that feeding method technique is additional when compared to the microstrip when coming to the DRS, right? The ideal radiation efficiency, generally radiation efficiency is around 70 to 80% in microstrip, but here it is 95%, more than 95%. You might get it. Next. So there are different excitation schemes. The microstrip line feed, you can place DRA on directly on the microstrip feed line. Next. So these things are almost common, but only thing is the placement of dielectric resonator should be symmetric across the patch configuration. I mean the antenna configuration, that you have to take care of. See, slot is exactly at the center, and the DRA is semi hemispherical, and it is placed exactly on the center of the antenna, and it is excited through aperture. The aperture, through aperture, the electromagnetic energy is fed to the DRA, right? Next. The coaxial forward profit that I have shown earlier, cylindrical DRA, the similar in nature. It's not only you can attach directly to the antenna, but you can also penetrate into the DRA, right? Next. So this is the configuration. The DRS can be placed on a substrate, can also be placed on the metal ground, because earlier in the 1980s and 90s, the DRS are manufactured on directly on the ground plane, because it's a ceramic material, because it's not a metallic material, right? So directly you can bring in contact with the ground, and but the proper care should be taken that the feed should not be in touch with the ground plane. So feed only in touch with the dielectric resonator, right? Next. So this is the fabricated of the earlier figure what I've shown. It's a aperture feed antenna. Next. So this is array of antenna. So this 16 element DRA is excited with the aperture coupling, that is through microwave feeding network. Next. And then this is conformal strip feed. You can use an embedded feed, like you're going to have a probe and you're going to have a metal patch, both together you can bring it, and the metal patch is going to be conformal across the DRA, and you can exit, right? Next.